Welcome back to our continuing study of energy conservation. We focused last time strictly on mechanical energy. Today we're going to take a broader look at energy. We're going to zoom out essentially and consider some other types of energies. We're going to consider the presence of non-conservative forces and how that affects the energy of the system. Let's get started. On the screen you see the simple example of a ball being dropped. Let's look at this from a mechanical energy perspective. If we measure our height from the ground, at the beginning, all we have is GPE, and at the end, all we have is KE. Okay, all the GP at the top is converted to kinetic energy at the bottom. Now, this is assuming the absence of air resistance. Consider, however, what would happen if we did have air resistance. Okay, what you would have, I think you would realize then, is that we would lose some kinetic energy at the bottom, right? In other words, it wouldn't be moving as fast at the bottom as it would be without air resistance, okay? And that's because the air does some work on the ball. And drag is a non-conservative force, right? So it's going to take some energy from the ball out of the ball and out of the system of the ball, so to speak, okay? So that this here would no longer be true. Right? What would be true is this. We would have GPE equals KE plus whatever work was done by air resistance or drag, right? The work done by drag. However, what we found experimentally, okay, what scientists have found experimentally is if you zoom out, right, if you don't just consider anymore just the ball as your system, if you zoom out and now consider as your system the ball and the surrounding air, and you measure the temperature difference of the air as a result of the ball plowing through it, right? The ball will hit molecules, and molecules will get kinetic energy transferred to them from the ball, and those molecules will then move faster, which essentially means that the air has heated up, right? So if you consider the thermal energy change in the air, energy is still conserved, okay? We no longer have mechanical energy conservation, but that's because we had a non-conservative force acting, right? So whenever you have a non-conservative force acting on a system, you're no longer going to have mechanical energy conservation, but fortunately, we're still going to have energy conservation as a whole, right, from a sort of a universal perspective, if we consider other types of energy like chemical energy, thermal energy, and so on. Let's go ahead and write these things out formally on the next screen. Okay, so when only conservative forces are acting, then you're dealing essentially with mechanical energy, okay, and this is going to be true, which we knew from the previous unit, the previous podcast. Now, when non-conservative forces are acting, right, you can still write energy conservation, but you're going to write it like this, and you're going to realize that the energies involved could be, they could be mechanical energies, okay, they could be thermal energies, they could be chemical energies, they could be other types of energy, nuclear and so on. Obviously, we're not going to consider nuclear energy right now, but basically, that's how this changes. We just have to zoom out and consider some other types of energy. You can apply energy conservation to the work energy theorem as well, or we actually can go from here, right, the work kinetic energy theorem to this right here, okay, where the energy of the system is the change in thermal energy, the change in chemical energy, and so on. An example of change in chemical energy would be with respect to your body, right? You're eating food, and you're expending that chemical energy that's stored in your body to do some work. So that's this is another way here to express energy conservation is by applying it to the work kinetic energy theorem, expanding it, considering other types of energy. Right, one way to transfer energy into or out of a system is to do work on it. Right, when you do work on a system, you change the energy of that system. Finally, we'll write this one more way, and that is if you consider a system that has energy being transferred into it, right, you're doing work on it, but then there's also energy leaking out of it. You can write energy conservation this way. E in minus E out equals the energy change in the system. Okay? Remember, the total energy of the universe is constant. Energy is neither created nor destroyed, only changed in form. If you find that your energy is not being conserved, all you need to do essentially is zoom out and consider some additional kinds of energy. Let's look at a specific example of when another type of non-conservative force is at work, and that is the force of kinetic friction. When kinetic friction does work on a system, it's essentially going to, you might think of it as sucking energy out of the system or dissipating energy, mechanical energy in the form of heat. This is an example taken from your textbook. Okay, you have a modified Atwood machine, a block connected to another block, and we're going to compress the block on the top 30 centimeters to the left. Okay, we're going to let it go. So the spring is going to push on that 10 kilogram block, and gravity is going to pull down on the 2-block system. So what we want to find out is when the 8 kilogram block has fallen 50 centimeters, what's the velocity of the blocks, right? Remember, the velocity of the blocks, they'll be moving at the same velocity, right, because they're moving as a system. So let's look at this from an energy perspective, right? We're going to set up our energy conservation situation here. Okay, we have energy at the beginning, energy at the end, and let's just write it. First of all, let's ignore friction, right? We're going to get energy dissipation, okay, right here, right? Energy is going to leak out of the system because of the friction that's happening there. So, but let's ignore that for the time, and let's just make sure that we're clear on just how to set up the initial energy and the final energy. So initially, well, again, before we can make any GPE determinations, we have to be clear about where our GPE level is. So just to mix it up, we're going to call our 0 GPE level right here where the block is originally. Okay, we'll call that height 0. And you'll notice that the block on the top is not changing its height, so its potential energy isn't going to factor in. So if we call that equal 0, then at the beginning, do you see all we have is 1/2 kx squared, right? All we have is the potential energy of the spring, right? Neither block is moving at the beginning, and we're saying that the 8 kilogram block is at 0 height. So all we have at the beginning is is EPE. Now, 50 centimeters later, right, we're going to have kinetic energy from both blocks. Okay, we'll write that as one term, right, because they're moving together. Okay, kinetic energy. This 8 kilogram block here, right, will have lost height. It's going to now have, call this M8. It's going to have a change in potential energy, but it's going to be negative, right, because we'll have dropped below the 0. So that's going to be a minus. Okay, so that's what the energy would look like. The energy equation would look like if there were no work being done by kinetic friction, but there is. Okay, and I think you see that that's going to subtract additionally, right, from this side here. Okay, it's going to leave less energy for the right side of the equation, the final energy. The question is, where are we going to write that term in? I'm going to write it on the left side or the right side. Well, you can do it either way, depending on which way makes more sense to you. So remember that the friction force is doing negative work, right? So one way to think about it is this way. Okay, you can add it to the left side, right? 1/2 kx squared plus the work done by friction, which is going to be negative if you pay attention to your signs, equals the right-hand side of the equation. That's one way to think about it, okay? So this essentially is going to look like this, 1/2 kx squared minus work done by friction, right? In other words, it's going to make the left side of the equation less, okay? The other way to think about it, okay, is to add the term to the right side of the equation, okay? So it would look like this, 1/2. I suppose I should change the M1 and the M2 to be consistent here. Let's make this, let's see, we'll make this M8, right, because I was calling that M8, and we'll call this M10. So M10 and M8. All right. So we still have this. We have that change in that negative change in potential energy to GH, and then we add the friction, the work done by friction to this side, right? So on the right side it becomes a positive term. What you might think of it as is in the following way. You have all this potential energy here, but it gets split between the kinetic, the potential, and the work done by friction. Okay, so if you add it to the right side, it's going to be positive. If you add it to the final, it's going to be a positive number. If you add it to the left side, it's going to be a negative number. I think you see that 6 of one, half dozen of the other. That does suggest an alternate way to write this that might be a little less confusing. Let me write that on the next page. Okay, another way to think about it, and remember, this is using another form of the energy conservation equation. That is the final energy minus the initial energy equals the change in energy of the system. Right? So mathematically, you're going to get the same thing that we have on the other page. But basically, the final energy was the kinetic energy of both, right? And minus the GPE of that second one, which fell down. Okay, that would be the final. And then minus the initial, which is the EPE. Okay, the difference between those two, that's going to be equal to the work done by friction. Okay, so maybe this makes more sense to you. I've given you 3 different ways to solve this problem, 3 different ways to think about it. But mathematically, it's all going to work out to the same thing. Okay, before we move on from this problem, let me do one more thing just to clarify, and that is the work done by friction. Just a little refresher in that regard. Let's look at what the right side of the equal sign is going to look like. Okay, so the work done by friction, remember, work is a force times displacement. Okay, and in this case, the force is a force of friction, which is mu times the normal force, right? And the normal force in this case, right, if we do a free body diagram for the block that's up against the spring, because that's the one that's experiencing the friction, right, we have the normal force up and the weight of the 10 kilogram block down, mg, right, and then we have, the spring force to the right, and then the friction force to the left. So that friction force there, right, that's equal to mu n, and you can see that the vertical forces are balanced, that the normal force is equal to the weight. So this is going to look like this: mu mass of the 10 kilogram block times 9.8 times the displacement, which in this case is going to be the 50 centimeters, right? So that's what that work term looks like, the work done by friction term. And remember that even though this includes a force, it's a force times a distance, so all of this is going to work out to joules. Okay? All right, one last example. Let's look at other non-conservative forces. Okay, we're just going to look at this conceptually. What if other non-conservative forces are working besides kinetic friction like we just studied? For example, sometimes no work is done on the system, and something else is going on. Okay, let's look at 2 examples here of incredibly awkward man. Okay, in the first case, okay, you might be kind of surprised here, but when you walk, okay, when an incredibly awkward man walks, he pushes back on the ground, and the ground pushes on him, right? And that's the force that propels him forward. So there's a force here, okay, that way. But you may be surprised to know that that force does no work, because at the point of application, right, which is the foot on the ground, there's no displacement. Okay, so there's actually, even though the force propels, accelerates the person, that force does no work. That force of friction does no work. And so what you have actually, right, if we use this equation here, okay, what you get is that the work done on the system is 0. Okay, the work done on the system is 0. And remember that that I'm going to change that side of the equation. This side here, right, is equal to E mechanical plus E thermal, right, plus E chemical. Okay, and so what we get is that the is that the mechanical energy, okay, the kinetic energy change of the person is going to be equal to the negative of thermal and chemical potential changes, right? This is an example of the chemical energy in your body going to move your body. Okay, it's chemical energy being converted to potential energy.